All right, so today's class we're looking at topic 4 on oceans. So like we talked about when we first started this unit, oceans, they cover 2/3 of Earth's surface. So when you look at a map of the world, you can see oceans, right? They dominate the planet. All of the world's ocean water, it is connected. All right, so oceans, they cover about 70% of Earth's surface, or about 360 million square kilometers. And the total volume of the oceans is about 1.3 billion cubic kilometers. So let's take a look at this first diagram here, looking at the salts. All right, so we're looking at the ocean water, 96.5%, and here the salts, about 3.5%, and then all the different salts that we see. So sodium is about 30.6, chloride 55, and then we get into the much smaller amounts here. So traces of almost every chemical substance on Earth can be found in the seawater, including gold and silver. But again, like I said, in very trace or very extremely small quantities. So on average, like if we had 1,000 grams of seawater, about 35 grams of it, there would be dissolved salts. That gives us parts per thousand, 35 parts per thousand, or ppt. The most common material in this solution is sodium chloride, which is table salt. The concentration of sodium in seawater is about 16,000 times greater than in fresh water. And then the next most plentiful salts are composed of sulfates and magnesium, calcium, and potassium. And when we use the word salinity, that is the measure of the amount of salt that's dissolved in a liquid. So where is the salt coming from? So salts are coming from the rocks on the land. So rivers and groundwater, as they're flowing over rocks, they pick up the salts and carry them to the ocean. As well, molten lava and gases from volcanic eruptions on the seafloor, they're also adding materials such as chlorine and sulfur to the seawater. Gases from volcanic eruptions on land circulate first in the atmosphere. So from there, they may also dissolve directly in the surface waters of the ocean or be carried from the atmosphere in rainfall. Looking at the ocean floor, looking at ocean basins.
Sorry, I'm here now.
So just looking at ocean basins, so these are the deep, wide depressions in Earth's surface that contain the oceans. The origin and formation of the ocean basins are due mainly to the movements of Earth's tectonic plates. As those tectonic plates move apart or together, some oceans expand while others shrink. So if we look at this diagram here, we can see the ocean basins that contain lots of different things we can see here, like mountain ranges, there's valleys, there's wide plains. So that's the ocean floor. Looking at ocean ridges, these are the long undersea mountain ridges. They're the youngest areas of the seafloor, and they are still being formed by volcanic eruptions. So molten lava will flow from those ridges, harden into new plate material that pushes tectonic plates further apart. Trenches are the narrow, steep-sided canyons that run along some ocean floor margins. And these are formed where the edge of an ocean plate pushes against the edge of a continental plate. As the plates move together, the ocean plate is forced to bend steeply down beneath the heavier continental plate. The deepest trench, called the Marianas Trench, it extends 11 kilometers below sea level. Here we can see abyssal plains here and here. So again, on the deep ocean floor, they are the wide open flat plains found between high mountain ranges at the center and the deep trenches at the edges of the seafloor. Next, we're looking at continental shelf and the slope. So the continental shelf, it's the gradually sloping area between a seacoast and the edge of an ocean basin. Ocean basins, they don't begin at the coastline. They begin many kilometers out at sea. So the area between the coast and the edge of the ocean basin, it's a submerged part of the continent. It's called the continental shelf. Next, we see the continental slope. That's a steep slope that divides a continental shelf from an ocean basin. All right, so ocean basin starts here. Continental shelf and continental slope makes up the continental margin. So next, ocean waves, large ripples that are set in motion by steady winds. Even on a calm day, there is a steady movement of smooth waves near the shore. Those smooth waves are called swells, and they're caused by winds and storms far out at sea. Common features that we've seen already when we were talking about light. So water waves, they have the features that are in common with all the other types of waves like sound waves, light waves, radio waves. We have the height, the wave height, which is measured from its crest, which is the highest part of the wave, to its trough, which is the lowest part of the wave. So here's the crest, there's the trough. The wavelength is measured from the distance of one crest to the distance from one crest to the next crest. The speed of motion is the time required for one wave to pass a given point. Okay, so breaking waves. So when a wave reaches shore, it will change shape. As the trough of the wave touches the beach, it gets slowed down by friction. The crest of the wave will, however, continue moving at the same speed. The wavelength shortens, the wave height increases. So the crest of the wave, it'll outrun the trough and it'll topple forward. And it's called a breaker. That's when the wave collapses on shore in a tumble of water. So usually surfers will use that forward motion of the crest to ride a wave to shore. Okay, here we could just see a diagram here, or sorry, a picture as a wave approaches the shore. Its wavelength decreases, its height increases, and then it collapses on shore as a breaker. How waves can change shorelines. So waves can shape shorelines by eroding and redepositing sediments. So waves, they usually collide with the shoreline at slight angles, which creates a long shore current of water that runs along the shore. Shown here. Long shore currents, they're going to carry lots, like many metric tons of loose sediment, and they act like rivers of sand in the ocean. If a longshore current isn't carrying all of the sand, then it has the energy to carry it. It'll use this extra energy to erode more shoreline sediments. Waves will slowly wear away the rocks. They can eventually form hollows. Over time, the hollows can enlarge. They can become sea arches or caves. So again, by that erosion, by waves and wind. If too much erosion occurs, overhanging rock may fall off into the ocean. Rock fragments broken from cliffs are then ground into sediments by the motion of waves. Those sediments are then transported by longshore currents. Seawater can also dissolve certain minerals in rock, which will increase erosion by chemical action. So there's that combined action of waves as well as chemical processes that can erode areas of rocky shorelines, sometimes as much as 1 meter in a year. Beaches, how are beaches formed? So again, all of that weathering and erosion. We have rock fragments that are rubbing against each other, and those rock fragments get smoothed and ground down into smaller pebbles and grains of sand. Along steeply sloped shorelines, these rock fragments will wash back into the sea. This will leave a shoreline of only bare rock with scattered boulders and larger stones, but where the shoreline has a gentler slope and calmer waters, those smaller rock fragments can settle and build up and form a broad beach. So there can be a range in size from fine grains of sand, which are like less than 2 millimeters in diameter, to pebbles and even small boulders. This is just showing sometimes barriers are put in place along some shorelines to protect the beaches from erosion. Okay, so I'm going to pause here. So the next part of this topic on oceans is we're looking at tides. So tides, these are the slow rise and fall of the ocean surface. It's caused by the gravitational pull of the sun and the moon, but the sun is much farther from Earth than the moon is. So the tidal movements that we see, they result mainly from the pull of the moon's gravity on the ocean. The sun has less than half as much influence on the tides as the moon does. Despite the sun's much greater size, it has to do with the distance. So spring tides, these are the largest tidal movements that occur when Earth, moon, and sun are lined up. So we can see here spring tide happening. Neap tides, these are the smallest tidal movements that occur when the sun and moon are at right angles to each other. A tidal range, this is the difference in the water level between high tide and low tide. So it varies with the shape of the shoreline. Okay, so those spring tides that we talked about here, they occur twice per month at full moon, when Earth is between the moon and the sun, and then at new moon, when the moon is between Earth and the sun. And then here when we're looking at neap tides, they occur twice per month during the first quarter phase and the third quarter phase of the moon. Okay, so as Earth turns on its axis, different locations on Earth's surface face the moon. So the result is a sequence of high and low tides that follow each other around the world. On many of Earth's shorelines, tides will rise and fall about twice a day. Okay. So the moon's pull causes the ocean to bulge on the side of Earth facing the moon. At the same time, there's a second bulge of water on the side of Earth that faces away from the moon. That second bulge is occurring partly because the moon pulls more strongly on Earth itself than on the oceans on the far side. So it leaves a bulge of ocean behind. So L here is just representing low tide. The H is representing high tide here. So high tides occur on the side of Earth closest to the moon and on the other side farthest away. Okay, next we're going to talk about ocean currents. So a current, this is a broad continuous movement of water in an ocean or other body of water. An ocean current, it's like a massive river within the ocean. So like a river, a current flows in one direction and connects in one place with another. Okay, so we'll talk about surface currents. Currents of water at the ocean surface, they are driven by winds. The steady flow of currents results from major wind patterns. These wind patterns blow in fairly constant directions around the world. So here we're looking at the winds. They're shown by the orange and red arrows. So what you'll notice here, like this, here's the equator. And what you'll notice is in the northern hemisphere, those winds travel in a clockwise direction. So clockwise in the northern hemisphere. In the southern hemisphere, those winds are traveling in a counterclockwise direction. Okay, so keep that in mind. And then what we see here also are also these blue arrows. So notice that the ocean currents, which are represented by those blue arrows, they're moving in the same direction as the winds. Okay, so there's three factors that influence the direction of winds and surface currents. Firstly, the uneven heating of the atmosphere. So warm air, as we know, it expands upward and outward because particles are moving farther apart. That'll produce an area of low pressure. Cool air with a high pressure will move into the area of low pressure, and then that moving masses of air creates winds. Secondly is the rotation of Earth. The rotation of Earth, it produces a deflection or bending of movement currents, and when you do that, you'll do a brain pop activity on it next week, and you'll see the Coriolis effect. So as wind and water currents flow over Earth's surface, the planet turns beneath from west to east, and that motion causes currents in the northern hemisphere to turn to their right relative to the Earth's surface. In the southern hemisphere, the effect causes currents to turn to their left. So overall result is that when winds along the equator, they blow from the east. Those are called trade winds, and they're pushing ocean currents towards the west. Towards the polar regions, westerly winds will drive currents the opposite way, from west to east. The third factor is continents. So moving currents, they're forced to turn whenever they meet a solid surface or the continent. So these continents will deflect east-west currents, either north or south. So it's the combined influence of winds, continents, the Earth's rotation that keeps ocean currents circulating clockwise in the northern hemisphere and then counterclockwise in the southern hemisphere. So again, shown by those red and orange arrows. Next, we'll look at ocean temperature and currents. So water temperature does not decrease steadily with the depth. It actually changes sharply to form three distinct layers. Warmer, okay, at the top, water is warmest near the surface. Almost all the heat in the ocean comes from the sun. Winds and waves, they'll mix the heat evenly through the surface waters, forming this mixed layer. The sun's energy does not penetrate very far. In this thermocline region, we can see a region of rapid temperature decline. Okay, so we can see the depth here on this y-axis. Our x-axis here is showing our temperature. Okay, so we can see like that decrease happening. Oceans and climate. So surface currents in the ocean, they carry heat from one place to another. Warm currents will begin near the equator, where the sun's heat is most intense. And then as these warm currents circulate, they affect the climate as well as the sea life of the regions to which they move. So the Gulf Stream shown here, it's a current of warm water. It starts in the Caribbean Sea. It flows north along the east coast of North America. It'll then turn northeast. It'll cross the Atlantic Ocean. This Gulf Stream, it carries warm water to Iceland and the British Isles. The warm ocean currents will affect climate because they will transfer their heat to the atmosphere. These warm currents will flow from the equator. Next is heat capacity, which we talked about a little bit in Science 7. Water, it has a very high heat capacity, which means it takes a relatively long time to heat up or cool down. So because of this, large bodies of water, they act as heat reservoirs in the winter. They'll remain warmer than the land nearby. This difference in temperature between the water and land affects the weather systems near the shoreline. So these systems will produce breezes that alter the processes of evaporation and condensation near the shoreline. Cold currents will flow from the Arctic and Antarctic regions. These cold currents will also affect the climate by drawing heat from the air. The icy cold water will carry icebergs from the far north into the North Atlantic Ocean. All right, I'm going to pause here.